My name is Gräler, and I will do this tutorial together with Andy McKenzie from NIWA and Martin Pontius, also from 5to N. And I'll try to give a brief introduction, and then we hand over to the next speakers. So why data access is so important? So data is generated in various geospatial fields all over, from hydrology and Earth observation, and also mining data, tracking data, traffic data, all kind of data is gathered. And so it's stored in many different flavors of databases and data access hubs. So once we have a standardized API, we can open up these data silos. And that's kind of the motivation behind many OGC standards. So we have the SOS standard to access the data, more modern versions of 10 things, APIs, also web feature services, web coverage services. They contain data that can be accessed and further analyzed in the further process. Of web mapping service presenting data more in a visual sense, less suitable for really accessing data for further calculation and manipulation. And there are currently new updates from the OGC. So we have the OGC APIs, which is kind of has a common part and special parts for features, maps, processes, coverages, and so forth. So this is going to be a REST JSON-based update of the former standards to make accessing data through the OGC APIs even easier and more lightweight than it used to be in the past days. But this will take 1 year about really to be functional across all the products. But it's also important to have like software internal APIs, like a common native exchange format, which, for instance, for the R universe has been SP and now moves over to SF. So if you have spatial data and you have a common format that can be used by all the analysis packages kind of addressing data and data storage and data access, it's very handy to have a single format, so it's just many-to-one translation instead of many-to-many translations if you want to move from one analysis step to the next analysis steps. So that's kind of important about the APIs we use and the APIs we have inside the software solutions we use afterwards. So the first step is always data visualization that we do. So you can have a kind of lightweight web interface, like further the 5to N Helgoland that you see in the screenshot. So you can select points on a map and look at the time series data and compare time series data for different phenomena, for different variables. You can also have local clients like QGIS and ArcGIS, which also have an SOS adapter, so like a plugin, and you can retrieve data there directly, or you can put it into your analysis framework like R, Python, or build a bridge to Grafana to visualize the data locally, or also kind of build web applications based on that. That's always the first step. So you already start to understand and to better understand what the data is all about and how it's related to each other. And here's kind of small examples from a slightly different topic, kind of the power of visualization. So this is forecast models of climate forecasts for different decades. This is kind of an app you can use. There's a link below. And on the left-hand side, you can select one decade, and on the right-hand side, you can one decade, and you compare these two decades with each other. And so we can see over the annual run, so these are different models and different runs of the models. So we see some variations in the model predictions, and you can kind of compare the two different layouts. And here we're comparing the variable temperatures, and the blue one is kind of the future prediction, and the red one is like our current decade, or already past decade, 2000, 2010. And now you see the lines, but you can also kind of select subsets of time. So you can sub-select some months, and you can do this kind of histogram overlays, and there it gets even more apparent that you have a shift of warmer temperatures for the kind of predicted cases, but you have kind of similar spread, and you get this kind of bimodal representation. And now if you would start to kind of reduce the time frame and look at it, it's really a tool to explore the data set and to explore these forecasts in the sense which kind of based on past observations that we see, and also kind of future forecasts for the future. And it's nice to really, you start to feel the data and to better understand the data, especially if you kind of narrow down the temporal window that you're looking at and moving through the year, then you can really understand what these forecasts might mean. And you also see, of course, that there's a huge uncertainty associated to it. So it's not just one single prediction. that we can kind of expect to happen, but it's kind of a set of years and a set of predictions that kind of might all be in a range. So that's important to understand for these predictions. It's not just a single true value, but you get a series of predictions. Just as an example for visualization works. But of course, you can add other sources here as well. And to kind of make it easy to get data into analysis framework, you need some API clients. And here in this tutorial, we'll talk about the SOS4R and the SOS4Pi API clients for R and Python. And of course, what's kind of the most interesting part about the looking at multivariates is the dependence of variables. So it's key for prediction interpolation. So all these prediction interpolation processes are just based on dependence and how the dependence between two variables or one variable over time from one time step to the other is designed and built up. It's all kind of hidden dependence structure. They're kind of easy approaches like correlation or regression models, which also can get quite complicated. And they're probabilistic models, like you can see on the right-hand side. And you see the scatter plots here. And if you draw a straight line through it, you might get an approximate, but you see there's kind of a bit more of structure behind the data than just fitting a straight line here. And especially if you go to this scatter plot, you also see there's still some structure in the data, but you won't find a simple model to represent this structure. So you will have to look at this probabilistic models that can describe these more or less complex structures of dependence between two random variables, u and v. In this example, it's a cross-like shape, and you see some, well, you get some certain dependencies to it, and you can use it, of course. So a few brief words about SOS4R. It's implementation of the SOS API. We have an additional convenience layer which tries to hide the standards complexity. So you have simplified functions to really define the source, get the data, and use the data and get the features of interest. And this might make kind of shortens the scripts quite well. And it is on CRAN. It recently dropped off from CRAN because we had to make an update that we didn't hand in time. So please use the most recent version from the GitHub repositories. And the demo and example here in this tutorial today will be given by Andy. And then we have another tutorial on SOS4Pi. It's a pretty recent implementation of the SOS standard, and it has some convenience features hiding the complexity. It's part of PyPy, so you can use it directly from there or use most recent version also from the GitHub repository. And this demo will be given by Martin. So let's jump right into it. And I have to switch over to Andy.
Okay, can you see it okay?
Yep, very good.
Good.
Okay.
Okay, I'll make a start then. So thanks for the introduction, Benedict. So as Benedict mentioned, there's a package, SOS4R, that was a package developed by 52 North. I'll be showing how to use that to connect to an SOS and to explore the data there and how to download the data. And this is all within the R context. It'll be a short tutorial, so I'm thinking 20, maybe 25 minutes. So that's a warning for the next presenter. You'll be up a bit sooner than you think. A bit of background, you'll see in the bottom right-hand corner, there's a big NIWA symbol there. That's where I work, and you may not be aware of that place and what's about. So NIWA, it's an acronym of sorts, National Institute of Water and Atmospheric Research. It's a New Zealand-based research institute, currently 9:30 PM in New Zealand, so I'm heading towards a yawn state, but I'm still going strong. I work there as a population modeler, and that involves things like estimating the stock status for fish and all sorts of other marine type modeling. I have a broader focus, you might say, in terms of data science in the marine space, so all sorts of statistics, modeling and data analysis type stuff, and I use R for that a lot, and I run the R users group at one of the sites at NIWA. Now, how did I get involved with this, you might wonder? Well, there's another person who works at NIWA, Brent Wood, and he does a lot of GIS work and is involved a lot with environmental data and databases and the like. And he had some extra money, and combine that with the 52 North team, which I've listed there. So I will not try and pronounce the surnames. I'm not so good on umlauts, but at least I've got them in the names. And part of that, this program was to update an older version of SOS4R. And part of the update was to add on, as Bennett mentioned, an extra abstraction layer where the functions are easier to use, more straightforward, and also to make sure it's updated to version 2 of the SOS protocols. And my role in this is not so much as the software engineer, but so I call myself the package crash test dummy. I get the package, the latest version that's come out when it's been developed, and run it and use it to see how things are going and give feedback in that context. And in particular, when I was using the package and testing it, I was using it on an SOS for some NIWA climate data, which I'll tell you a bit more about and which I'll use to demo the use of the package. Now, the focus of this short tutorial, so I'm aiming at R users, or people at least somewhat familiar with R, as of course this is a package for R. And what I'm aiming at is to get some data off the NIWA climate SOS and use the SOS4R package to do this. It's actually very straightforward. The package was well made. Some further background in terms of what NIWA, you can see in the title of the Research Institute, we collect a lot of data for atmospheric data. There's a lot of we get a lot of marine data, freshwater data, but in particular we collect a lot of climate data. We have weather stations where a lot of data is collected from, and there's also a lot of stations that collect hydrology data from rivers and the like. I'll be concentrating on the climate data from some weather stations, and by climate data I mean the type of data they do collect are the obvious things like wind speed and temperature and pressure, but there's a number of other quantities that are also measured there and calculated from those stations. Now, how to get that data out, part of what NIWA wants to do is to make the data more accessible. This is the climate and hydrology data and the other data as well, and that's part of the point of this is SOS setup. Now, there's various ways of getting the data. One is browser requests, and I'll demo a bit of that and show that can be done, but it's not the easiest way of doing it. Another way is there's a free GIS program called QGIS, which I've used. It has a plugin which makes it easier to grab some of this data. I won't demo that. I haven't actually used the plugin, though I've used QGIS. What I'm going to concentrate on particularly is the SOS4R package. And I'll mention a bit about once you've got the functionality working in the package, you can then combine all the functionality together into what's called a Shiny app, which is essentially a graphical interface, and you can program that up in R to make what's called a Shiny app. So I'll mention that briefly at the end. That's a useful way to make things even easier to do these things. There's a link here which when you get this PowerPoint off me, you can click on. It shows you the type of data that is collected at NIWA. There's a whole bunch of stuff, and as I said, we're going to concentrate on the climate data from weather stations, and this is the web address for that. That data, it's collected, I think it's at an hourly interval. What's that? This SOS is stuff collated and summarized at a monthly resolution. So underlining it is actually much higher resolution data. The public face of what you see which at this SOS is data at a monthly resolution or summarized at a monthly resolution. Now, what's there? Well, you can go via the browser to see what's there. You can go and do this yourself and type in all these commands here. And I'll see if I can bring up I'll need a pointer at some point, so I'll bring one up now. Okay, so Simon gave a thorough introduction to SOS protocols and how you can use the browser type setup. But here's the SOS itself, or its location at least. And here's a bit more information about how what we're going to access, and it's version 2. And this is actually asking for something from it. This is asking what's actually there, what type of weather data is there. And what you get out when you do that is, and this is a brief summary of it here, you get out some bit of information here about what you were trying to do. And here's the actual data here, at least the start of it. There's a whole screen of it that keeps on going down the page. So you get this out in this, it's readable text. You can use text to ask for some information as a browser request, and you get text out. It's in XML format. Now, you can extend this the type of browser requests style, and this first example up here. What about for a station? And this is the name of it here. If you already know the number for it, what's the name of that station? There is a name associated with it, an actual location, and some lats and longs. So you can extend this browser request and ask for a bit more information about that particular feature, or in this case, it's actually a weather station with that number. I'm not showing the results here because it's just going to fill up the page a bit. So I'm demonstrating the type of browser requests you can use to get this information. And to actually get the data, well, similar sort of thing, syntax, you just extend that out, request for some actual data for that station. And what happens if you're asking for some particular, and here's a particular type of thing measured at one of the weather stations, or at least derived, it's monthly data, extreme maximum temperature on a monthly basis, and you're asking for it from a particular time period. And here's your browser request here. Good luck if you try to type that in and get that right. You might, after a few attempts, you probably won't. So you see, you can use browser requests to get the information, and it works, and the information does come out in a reasonable format. It's XML and is readable, but from a point of view of an R user, this is difficult. So, as I said, that you can get the information out. The syntax starts to become pretty horrible, and the output itself, well, it's at least it's text, but it's not directly usable for an R user. So the idea here is to instead use the SOS for R package to make it easier to get this, to explore this data to see what's there, to pull the data out and have it sitting in R ready to use. Alternatively, you can use the QGIS plugin, but for an R user, the SOS for R package. And when you've got the hang of the SOS for R package, you can then easily enough, with a bit more knowledge, make up an R shiny interface, i.e. a graphical type interface, to make it even easier to do this type of stuff, to explore the data. Now, in terms of installing the package, so to get the latest developmental version, you can get it from GitHub, and here's one way at least of getting it. There's various ways of getting it out, but this is the way you can get the latest developmental version out here via that command. This is an R command here. If you haven't installed this packages called remotes, then take away this comment bit here and install that package. Away you go, and you can install the latest version of it there directly from GitHub. It's usually sitting on the Rcode package repository, which is easy to install from within R. As Benedict mentioned, there's just a few little things that need to be fixed up for that repository. What it's got sitting there at the moment. There's been a few little changes to R, so I assume to be back onto the Rcode package repository pretty soon. Okay, so let's assume you got the package installed. Now, I'll show you how to use it. So I'll go over a number of aspects of that. So one is part of the data exploration aspect. What phenomena are there? And in the context of the climate data, what climate data is available on that climate SOS in terms of wind, temperature, and all sorts of other quantities. Exploring sites, So what weather stations are there and where are they located? So how do you do that? Once you've done your exploration, you want to download some data probably. So how do you do the data download? And then you've got it into R. What can you do at that point after that? And the package is well set up in the sense that when it brings the data in, it's in a format where you can easily plug it into GIS type packages for plotting up spatially where things are and also doing time series plotting. So it's set up in such a way that it's all ready to go for spatial temporal analysis. Now, go straight into exploring phenomena. Now, the first thing you've got to do, of course, you've got to bring your this package in. So that's that command there. This is all R commands here, library SOS for R. And there's an initial connection process here in that next line. The SOS is the function. So it's saying where you're getting it from, some information about the binding. I'm not actually sure what this is. And version 2 is what you're using for the SOS. So the initial connection phase you do at the start. Now, first thing, okay, so what climate data is available there? Well, it's easy as, here's the command here. Phenomena, what phenomena is available here? And remember, that was that connection you set up at the start, my SOS. This is R, we're putting it into a R variable called phenomena, and you'll see on the next page what we've got. But STR, that's a STR is short for structure. It's going to examine a bit of what type of data do you have there, what's its format, and it'll display it a bit. Head, it shows the first 6 data items. So it's a quick way of seeing what you've actually got. Okay, so it's that's very straightforward, and what you get out. And I've shown the commands again at the top here. Get the data, what's the format of the data, and give a little brief summary of it. And it says, what have we got? And if you're familiar with R, it's a data frame, which is great. It looks like something like a spreadsheet might look like. There's 84 types of climate data there. And here's a little summary of them. They're all characters. This is what we've got, all sorts of things to do with winds and gales and frost and the like. Head, okay, let's have a cleaner look at the data. Not worried about too much about what the data format is. Just want to have a closer, just want to have a look at the first 6 data items, and head brings out that. Now, okay, so you've you know what climate data is there, part of the exploration process. What time period does that climate data cover? You might have, I think there was something there to wind gusts above a certain speed. Well, when does that start, that data, and when does it end? And that's something, an obvious thing to want to know. Well, that's easy. Same function as before. We're trying to explore the data from here. What phenomena are there? We'll include something extra, which is a temporal bounding box. So you know when that data starts and when does it end. And we'll have a look at the data here. And what do you get out? Okay. Same as before. Here's your phenomena, your type of climate data you're getting out. And when does that start from? 1960, and it goes through to this was an example done back in the start of May, so that's why it ends here. Otherwise it'll carry up to the current day. Okay, so you can see this is very easy to get out the to explore what data is there. Now, just digging in a little bit more. So what data is available, what time period does it cover, but we want to break that up by the separate weather stations. So some of the weather stations, that particular climate data might start later or earlier, or finish later or earlier. So this is going to be exactly the same as before, but broken up by stations. And you can see the syntax is easy. You just continue doing what you did before. Ask for the bounding box, and then ask to include the site ID, which means what is the weather station number. And same type of thing as you're getting at before, except you can see there's another column here, which is, so these are repeated. This is the same type of climate data, but you can see it's different stations and the begin and end at different times. This has been chopped, by the way. Normally this bit here, if you're looking at it in R, would be sitting over here, but it runs out of room on the screen here if I do that. Okay, so that's one angle to explore the data from, what climate data is there, and over what period of time does it cover. You can explore it from another angle, which is to look at what sites, or I would put it another way in this context, what climate stations do we have there. And you'll see, here's, so sip on some water. Here's a syntax to find out what sites you have there. That'll also bring out the location as well. And I'll show more about this later, but when it brings out the sites, it's a GIS type object. Well, it is a GIS type object in terms of our world. It's a spatial points data frame, and that's already to plug into various packages that know how to deal with that. You know, like GIS packages, you have GIS programs, you have GIS packages in R, and this object called sites that comes out the end, that's already to plug into that, and I'll show a little bit on that later. What do you get out when you do that? Well, here's sites, and this is what I meant in the sense that, just remember STR tells you a bit about the data structure, what's the data format, and as I mentioned, it's a spatial points data frame. It's got the data sitting there in a slot. That's a slot in the R world, R terminology, and there's the coordinates are sitting here. There's a bounding box, and the projection is here as well, sitting in that. If you ask for head, it ignores all the other stuff and just gives you the data with the coordinates and the site ID, i.e. station number. Okay, so you can ask for the sites with a straightforward command. Now, as with before, when you're exploring what phenomena were there, i.e. what climate data was available, and you had a function called phenomena, well, with sites, you can extend what you ask from it and it'll give you further information. So before I just asked for the sites and it gave the location and a number, you can ask it to include, and I've jumped a number of steps here, you can ask it to tell you what phenomena, i.e. climate data, is associated with the sites and over what temporal range does that climate data exist. And you get out a bit of a complicated object, but I've used the head to pull out the appropriate bit. And the sites are listed as before. You also get some other columns. So this column here is in fact sitting over here. This here, I've chopped it up, it's sitting over here. So you get a whole lot of columns out. The first column is the site ID. The next column is this one below here, which is a particular type of climate data. And it's got a temporal range. As it happens, it's in seconds here. I assume seconds since Unix time. Okay. So you can explore from the sites angle as well. So this is all part of the exploratory aspect. Now, if we go to actually downloading the data, so you can see exploring the data is straightforward. Downloading it. Now, there's a bit more going on here because you have to tell it a few more things. I've repeated the phenomena bit here, which tells me what climate data is available. And this bit here is just pulling out one of them. They've got quite long names in this case here. So this phenomena 18.1 is actually pulling out this here, as opposed to me having to type it in further down where I'm trying to pull out the data. And okay, so you want to tell it what climate data you want and a begin date and end date. Earlier versions of the SOS went via the pass data package, which has this function here for passing the dates into the format that it required. So I suspect from what I've seen on the GitHub in the latest versions that's perhaps changed, or perhaps both can be used, because I can see that's using the as POSIX CT, which is another way of putting stuff in a date format. Either case though, once we get down to here, this is the function that does all the work. Get data, you tell it about your connection you're using, what phenomena do you want, and I've done this instead of typing it out in detail here, what site and a begin date and end date. You can add extra sites on here as well, using the usual R syntax to set up a vector. And what do we get out? Well, here's the data. You asked for it from that site 1056, and there's a timestamp here, and there's some bits missing here I think as well, but here's the data one asked for, and here's the actual data itself. Right, now I mentioned that so I covered setting up an initial connection to the SOS, and exploring the data. You can explore that from the phenomena angle or from the sites angle. And I mentioned that when the data comes out, it's set up in such a way that it's ready to use. If it's spatial data, it's ready to use in packages that are good at handling spatial data. And so there's lots of ways of doing things at that point. Say you've got the sites out, you want to plot them. There's lots of packages, there's piles of packages, but here's a quick way of plotting up those sites. So just remember before, I was pulling out the sites and it pulls out the coordinates. It's a GIS object, spatial points data frame. Okay, well there's a package called map view that'll is ready for that type of data to be plugged in and plotted. And so you can go map view, put the sites in, and some other bits and pieces here. Don't give a legend, and color the regions in blue. And it gives out I was just reminding the fact that it's a spatial object here, and you can get a map out in one line there. And this one you can zoom in and out, etc., and do a few other things. This is just a demo of a way to make a simple, quick map once you've got that information out. And time series. Climate data naturally has a time aspect to it, and so it'd be good to plot up time and whatever it is on the y-axis. So we'll go back to that station 1056, did that data download, which was an extreme maximum temperature, and plot it up. And there's lots of packages for plotting, but we use this one here. I'm trying to use a similar one that 52 North have used in their examples. So it's like revision when you see it here, and then you look at some 52 North examples. It's the same package. So XTS, that'll plot up time data in a quick, easy way. Here's the data. The actual data is sitting in the third column. So that's why I'm pulling that out. And here's the actual time here. Here's the actual plot here. That knows, this just simply says plot, but because it's a time series object, this is what this is all about, setting up a time series object. Here's the time series object. I don't know how to plot that when you just go plot, and it plots it up here. Here's the time, and here's the maximum extreme temperature. So it's just a quick, simple way of doing a plot. You can do all sorts of other things once you've got data that's in a time series format. And I was looking at the time. Oh, yep, I'm doing pretty good. And the R-Shiny package. So that's a way of, this is a way of, within R itself, it's part of the R language, a way of programming up, and I put in quotes, a website, so you can run it from R itself, and it looks like you've got a website, but you haven't really. You haven't actually pushed it out into the world where other people can look at it, but you can easily enough do that. But it's great for interactive data visualization. You've got multiple variables, and you're trying to select by different aspects of that. In this case here, we're looking at, we've got different phenomena, different sites, different time periods, and you're trying to dig into the data via those 3 dimensions and explore the data. And this isn't a tutorial on Shiny itself, but you can go to that link there and you'll find out plenty about it. I won't demo the package, but I'll say a little bit more about it. It's it doesn't require a lot of coding because it's designed to it's designed to set up an interface in minimal amount of lines of code. This particular one here, just made a prototype package, as I've called it. I've used Leaflet, which is a great program for plotting weather stations. You can zoom in and out. It makes really nice plots. It's not just this is not just an R thing. This is JavaScript, and turns up in other languages as well. Date package. It's great for dealing with dates. It's got some intelligence. When you're dealing with date information, often you have to tell it what the separators are and all sorts of other stuff. It goes and figures a lot of this out. It saves you a lot of hard work. DPLYR, ggplot2. These are modern packages which are very good for data manipulation, particularly filtering data and making very nice plots. Shiny has some default tables and they look pretty good, but there's a package called DT to make even nicer tables. There's some other good aspects. Here's what you get out when you knock together those packages and a bit of code. You can select the phenomena here, select the station, select a date range. This is a static image here. On the right-hand side here, you can select the stations and see the stations by clicking on them. So at the point you're happy with the data station and phenomena you've selected, then you can look at the data, brings out a data table, and then you can do a plot. And in either case, you think, I like what I've got, I want that data, well, I like that plot, you can download the data and save the plot. There's some idiosyncratic aspects here on this regarding subsetting data, but I won't go into that. There's some bits and pieces I want to tidy up on some of this. But you can go and have a play on that app if you wish. Okay, I'm finished there, I think. Yep, I've done pretty well on the time. So please feel free to get hold of me if you want to get hold of code. You've got the PowerPoint here, but I've got all the code sitting in a separate standalone script. So you haven't got all the other stuff in the PowerPoint there. So you can get that off me if you wish and go through that. You can grab the code off me for the R-Shiny app and do as you wish with it, improve it, extend it in whatever way you wish. And I think there's a nice transition at the end here. I go to the, I'm sure you see at your end, but yes, we get to the end with that. Okay, I've finished.
Okay, thank you. Thanks a lot, Andy, for joining us late at night in your case, and for this nice presentation.
I'm still awake.
Very good. I think if there isn't any pressing questions, by the way, we can postpone them to the end if you're still with us.
Yeah, I'll stay on. Yep.
Perfect. Thank you.
So I'll stop sharing here.
Yeah, stop sharing, and we switch over to Martin.
Okay. Hi. Can you hear me?
Yeah. So you can start share your screen right now.
Sharing my screen. Yeah.
Perfect. So we're now switching from R to Python, and kind of there are huge parallels between the content, so from the kind of application side, but of course it's a different language, a different flavor, and a few additions to it. So here you go.
Okay, can you see the slides?
Yeah, perfect.
Okay, perfect, thank you. Yeah, hi everyone. My name is Pontius. I'm a software engineer at 52 North, and I will guide you through the next part of the tutorial. Yeah, the topic is still the same, of course, accessing environmental time series data for data analysis. I will focus now on Python and specifically GSV2020 package. Okay, just I have a few slides only, and afterwards I will show a live demonstration with the Jupyter Notebook. The Jupyter Notebook is also available on GitHub, so if you want to try it out and play a little bit with it, you are very welcome to do so. I will show you the link later to this notebook. Okay, so just a short reminder of the motivation. Yeah, we have the SOS standard, and we can use it to share sensor data in an interoperable way over the web. But of course, if you have, once you have shared the data, you don't want to stop there. You want to do something with the data, you want to make it useful. So you need some kind of framework to analyze and visualize the data, to really exploit the full potential of it. So we have already seen how you can do it with R, and now we will see how we can do it with Python. Okay, so on this slide, I want to introduce you to one of the existing libraries, source client libraries. It's called OWS-lib. It's a library not only for SOS, but also for in general for OGC web services. So we have also web map service, web feature service, and so on. I will show you maybe shortly the GitHub repository, and there's a link to the documentation of OWS-lib. So yeah, you can see there's a lot of OGC specific things are implemented that you can use. And here also some documentation, how we can use the package. Okay. So yeah, it offers a lot. For example, it offers functionality, how you can do the requests to an SOS service, how you can parse the XML data, and there's also a function get observation. So there's already a lot available, but there are some restrictions in this library. For example, some functions are missing. The get data availability function, the get feed of interest function, and there are really no functions for the metadata. You have to really check the object attributes to get the metadata, which is not very convenient. And also the get observation function is not very easy to use for people who have not so much experience with SOS or Python. For example, I have here an example how it would look like. You have this shouldn't be self, but it should be the DOS instance. So you have the DOS instance called get observation, and you get the response, which is the raw XML as bytes. So you can't really work directly with the XML. So you have to pass it into an XML tree, and then you have an object from the OWS-lib, DOS get observation response, and yeah, you have the path response now as an object of this type. But even though you have this object now, which contains your data and all your information, you still don't have an object you can easily work with in Python. Like usually you have a list, an array, or a data frame, or something like that. So it's really a couple of steps to take if you want to use OWS-lib directly. So in order to make it easier and to implement the functionality that is missing, we started a new package, Python package called GSV2020. It's largely inspired by GSV that was introduced earlier. So some of the interfaces and functions and the vocabulary conventions are quite similar, not completely, but inspired by thus far. The package is relatively new, so it was started in this year in May by Alfredo, who did his internship at 52 North this year. So he initiated it, and it will be further developed in the future as well at 52 North. I can show you also. Yeah, the Git repository. So you have here some explanation also what kind of features are included, and there's some documentation of the most important functions. For example, you can do connection to the SOS service, and here's some metadata functions and get data availability, get sites, so features of interest, and the get data, which actually download the data of some specific phenomena. So I will show these, how you can use these functions in the notebook later. This is just to give you a short overview. And the library is also on PyPy, those for Py. So if you want to use the library, you can just copy this command here, pip install those for Py in your console, in your shell, and it should directly install it into your Python repository. Okay. So what is new in Py, what is not included in OWS are the functions, as I mentioned, get data availability, get feature of interest, and some convenience functions, get data and get sites, where you can use it with, you need some knowledge, of course, but it's only a minimum knowledge expected of SOS. Okay, so here I have one slide just to list what requirements we have to run the example notebook. You need Python, of course. It's recommended to have a version 3.5 or higher. I have 3.6. You need Jupyter Notebook, and you need some libraries. So Py, of course. Then Pandas is a very basic, very widely used library for data science, data analysis, which offers a data frame object, which is quite nice to work with all kinds of data. Then matplotlib is a standard library for math and plotting. Seaborn is the library which is really helpful to plot statistical data. And then we have some other packages which are more or less helper. Okay, and of course there's some dependencies from these libraries here, which are installed under the hood. These are one example, which is important, GeoPandas, which is just a pandas library with added features for all kinds of geo data. Okay, so this is the Jupyter Notebook. Okay, this is the link to it. I think I will post it or share the slides. So if you want to test the notebook yourself after the presentation, you will have all the data available. Okay, so after this introduction, we can directly jump into the notebook. I will show you how you can use those for Py, mainly 3 topics. First topic is metadata. Second topic, spatial data, and the last topic is sensor data. Okay. Okay, so now I will demonstrate how we can use the package. First of all, of course, we need to load the needed libraries.
Sorry for interrupting.
So the
a bit larger.
Yeah. First, of course, you need to load the libraries. We are loading the Py library and a function from this library, connection SOS. And then I mentioned already before, matplotlib, Seaborn, and so on. So the first thing we have to do is we have to connect to an SOS server. Just executing it, okay. Then we have to connect to an SOS server. Now, in this example, it's a SOS server from the Wupperverband. So Wupper is a river in Germany. So it's a Wupper River Association. And this function will return an object, an SOS service object, which we call a Flux SOS. And this is a central object you work with. So all the methods I mentioned before, like get data, get sites, are methods of this object. So run it, okay. And before we actually work with the data, it's good to see what this SOS service offers you. So first of all, we check the SOS service identification. We have this metadata function, SOS service identification. We can call on this object, on the SOS service object. Okay. So we get this kind of metadata, the title, abstract keywords. In this case, we have keywords Gewässergüte, so hydrology, meteorology, so kind of water-related data is the topic of this SOS. So next, we can get some information about the provider. We have the function SOS provider. And yeah, we get the organization, the website of the organization, and contact data, and phone number, street, and all this kind of data. And then, yeah, as you probably already know, there are different kinds of operations provided by the SOS standard. And you can also inspect the operations which are implemented by the specific SOS. So not all of these operations are necessarily there for every source. So you can check if you can actually use the get observation function or the get feature of interest function. Okay, so next we can check the offerings. Okay, so what is the content of this SOS service? Now this prints you the whole list of offerings. Maybe it's easier if we just call the first object. Okay, now it's a bit easier to read. So in this example, we have Zeitreihen Einzelwerte, so it's German. I will translate it. It's time series single values, and we can see what kind of observed properties we have for this offering. This is, for example, electrical conductivity, air humidity, and more. You can see the temporal extent. It's the data started in 1990, and it's going until today. So it seems to be still in progress. You can also see the spatial extent of this offering as a bounding box and the spatial reference system used. Okay, so we can also get all the phenomena which are available. So also just as a list to have a quick overview. So yeah, we have here the humidity, air temperature, precipitation, oxygen, water level, dam water level, pH value of the water. So as I said, all kind of hydrological data. Then as the last overview function, we have the feature of interest, which prints you just a list of all the features. Later I will show you also a map. This is just a quick overview. Okay, because not all features of interest have really all these phenomena and all the offerings. You can have a more detailed description with the get data availability function. You can just use it without any input, and it will print you a really long list of all kind of data that is available. You can also pass more objects to restrict the request. For example, now I only request for the property water temperature, and I request for only 2 features of interest, which are 2 locations, Opladen and Bever-Talsperre. And now we get the data availability for these features of interest and the observed properties. So we see, okay, Opladen is here, so it seems this location doesn't have this property because it's not in the list. Okay. So this was it about the metadata. Now, in the next part, we will see how we can work with the spatial data. First of all, we download the data using the function getSites. GetSites doesn't need an argument. So if you don't provide any argument, we'll just get the list of sites and the geometry. This object, which is returned from this function, is a geodata frame. The geodata frame is just a data frame which an additional column called geometry. And the geometry stores Shapely objects. Shapely is just another Python library, and it handles all the different kind of geometries. So you can have points, but also polygons or other geometries. And if you want to include the phenomena, okay, if you set it to true, okay, next processing time, okay, you can see which phenomenon is available for which site. So now we have this Barmen, Wupperverband Hauptverwaltung, and we see that electrical conductivity is not available for this specific site, and but air humidity is available and air temperature is available as well. So it gives you a nice overview of the different phenomena and sites. Okay, you can also check the coordinate reference system, for example. Now this is EPSG 31466, and you can also change it. For example, in this case, so this 2CRS is a function of the geodata frame, and if you call it on the object, you can change the reference system, for example, to this one. And if you want to just check one specific row of this data frame, you can do this with ilog, which is integer location. You have to be careful if you don't use this. I think, yeah, it doesn't work because it expects a column here. So you would, for example, now you would get a column, and if you want to get a row, you need to use the ilog function. Okay. So now that you have the data, you have the names of the sites, and you have the geometries, you can plot the data. The geodata frame offers a plot function by itself. You can simply call it on your data frame and give the figure size, and it will print you this map. We need to wait a moment. Okay. So you will get a static map and the points as blue dots and a background map. You can also change the background map with the source parameter. So maybe I can demonstrate this too. So now I tell the function I want to use the OpenStreetMap space map. Okay, you see now a different basename. So this function of the geodata frame is pretty nice to get a first quick overview of your spatial extent, your spatial your sites. But of course, it would be nice if you could zoom in or do some interactive stuff. So in order to do this, we use another library, Python library called Folium. And yeah, you can see how it looks like. You can move around, you can zoom in, zoom out. You can add pop-ups to your sites, to your locations. Yeah, which is pretty nice, and I think much better than the plot function of the geodata frame. Okay, so that was it for the spatial data. Now we will see how we can work with the sensor data, with the time series themselves. We will call the getData function on our service object again, and we don't need to give any arguments. So this will work, but it can be very slow depending on how large is the data. So I really recommend to give at least one phenomenon or one site, one of these arguments here. But it should work also without any arguments. So you can use these 5 arguments: procedures, phenomena, sites, and begin and end at the time. So the beginning time and the end time. The format is the string for the time expected in this format here. Now we make a call for the phenomenon water temperature and a site obladen. We need to wait a moment again, okay. And we just print, so the return value of this function is a data frame. And we print just a quick overview with the head function and receive first 5 rows. We see a procedure, phenomenon, the timestamp, the value, and the unit. And now we have the data in an object that is easy to use. In a data frame, we can use all the Python functionality that is out there to really inspect our data and do something with it. Yeah, if you want also to inspect the data frame more, you can just, for example, use the unique function on a subset of on a row, on a column of the data frame for the procedure in this case. So we can see the unique values in this column, in this specific column. So in this case, we see there is only one procedure called single values. And here just have some subsetting calls for getting subsets of the data frame. For example, you can get the values which are larger than 5, or you can get specific sites or specific procedures. So next, now that we have the data in a data frame, we can plot the data finally. Okay, so this is working. We use matplotlib for this. So PLT stands for pyplot, which is a sub-package of matplotlib. And it's really a standard library in Python to plot data. So in this case, we have one feature of interest from our data frame. And here we're taking the subset for this specific feature of interest. We extracting the timestamp, save it as an X value. This is an array now. And we do the same with our value. And yeah, then we can just hand over the 2 lists, arrays, to our plot function and plot it, and of course some labeling. And now we have a really nice time series here for the water temperature at this specific site. So we see the time axis on the x-axis. It's from 1st January 2019 to 1 month long to the end of January. So now I'm showing another example how you can do the same with 2 sites. We could check the data availability before to find another site which offers this specific property phenomenon. So we use the get data availability function again, hand over the water temperature and the single values as a procedure. And now we can see this was the location that we used before, Opladen, and now we can download additionally for another location. So I choose to use this location here. So we make the same call as before, but now we change the sites argument here. So we added to Opladen, we added the site Laken. And now we make another request using the get data function. And we can plot a second time series here, just adding the same stuff as before for the other side. So now we have in blue the first side, the first feature of interest, and in yellow the second one. We can see there's some shift. So Laken is a little bit colder than Opladen. Maybe it's more in the mountain area. Now we could go back to the map and check it. Yeah, but I don't know where it is, so it will take some time. So I will just skip this. And if you're interested, you can do yourself using the notebook. So now we have seen how we can plot 2 different sites in one plot, but it would also be nice to plot two different phenomena for one site. So yeah, we could check again the data availability. I did this before, and I found out that we can use this site Bever-Talsperre, and we can use 2 different phenomena, which is air humidity, this one, and air temperature, this one. We needed to adapt the time because it's not available in the recent time, only in 2011. And okay, now we can see the 2 phenomena in one plot. On the left y-axis, we have the air humidity from 50 to 100% or even more. Okay, and we have on the right y-axis the air temperature from -10 to 10 degrees Celsius, and on the x-axis we have again the time. Okay, so in order to do this, we use similar plotting functions as before with a matplotlib, but we need to use this call here, strings, to bind the 2 axes together. Okay. So one maybe more advanced feature is data subsampling. Here I'll just call it first and explain later how it works. So you can see now we subsampled the data. It's much coarser, it's smoothed. Just scroll up as comparison, see much smaller variations here. And now we did the subsampling, smoothing. Okay. Now I will explain a little bit how it works. We set an interval for hours, and I'm getting the data frame for this specific phenomenon. So just remember, we have 2 phenomenons. I'm just saving the timestamp and the value. And now there's a function which is part of the pandas library. It's called resample. So you can see we have a data frame df1, and we call the resample function, which is part of the pandas library. We give it the argument interval, which is 4 hours, and we tell Python to use the nearest value. In order to do this, because we have different timestamps, and I noticed that some timestamps are duplicates. So this function resample doesn't work if you have duplicate indices. So that's why we do this processing before. We're grouping the data by the timestamps, and we aggregate. If we have a duplicate timestamp, we will just take the mean for this time using the aggregate function. And after this, we have no duplicates, and we can easily use the resample function. Okay. And the plotting is again as before, just the same code. So as last part of this tutorial, I want to show you the library Seaborn. So Seaborn is usually imported as NSS. It's a library which is really helpful to make statistical plots. Here I plotted the histogram. So for the data we have seen at first for this. So this was the air temperature, the water temperature for two sites. We can see it's correlating. And now we can analyze how large is the correlation, for example, of these two time series. So first we plot the histogram. You can see the first site has values between 2 and 8. The second feature of interest, the second site has values between 2 and 12. And yeah, we can see the distribution of the values. You can do this also in a 2D plot. So here we have on the x-axis the first site, on the y-axis the second site. And Seaborn has also a function called join plot. You can see here again the first site on the x-axis, the second site on the y-axis. Now we are plotting the water temperature, and we see, is there correlation between those two? So we calculate a regression, and we can see it's quite linear. So we can see the statistical value 0.9. So we have a quite high correlation between these two time series. And yeah, just to show you that you can have different style of this join plot, we can use hexagonals to organize it, to visualize it. We can also use the kernel density estimation to have a different view on the data. Yeah, okay. So that's from my side. I hope you have an impression how you can download the data using ZOS4Py and how you can use, for example, Matplotlib and Seaborn and Pandas to really analyze and visualize your data.
Okay, thank you.
Okay, thank you.
Thanks a lot, Martin. Very nice presentation, very nice examples of interesting plots and what you can do with the data once you have it in your analysis framework, just as for the R case. So we try to make these slides and presentations and the Jupyter notebooks available to you in a consolidated form somehow. So you'll be able to go back to it and explore parts of it if you like, and try it out yourself for your own service or for your own analysis that you would like to present and put forward. So if there isn't any question for now, thanks a lot for listening and joining in.